Hello, my name is Daniel, and today I'm going to be talking about separable equations. So what is a separable equation? Well, a separable equation is a first-order differential equation that can be written in the form dy over dx equals some function of x times some function of y. In other words, it can be broken down into an x component and a y component, as is the case here. Note how multiplying both sides by dx and then dividing both sides by g of y effectively splits the y's and the x's onto opposite sides of the equal sign. This is why they're called separable equations. So, for example, if I had the separable equation dy over dx equals y over x, multiplying both sides by dx and then dividing both sides by g of y, which is just y, so dividing both sides by y, would give us dy over y equals dx over x. And now I've separated the y's on one side and the x's on the other. From this point, how do we move on to solve for our original equation? Well, we can integrate both sides because integration preserves the equal sign. And this gives us the natural log of the absolute value of y equals the natural log, or plus some c1 equals the natural log of x, absolute value of x, plus some c2. And I can then subtract c1 from both sides, and c2 minus c1, I'll just call that c3. From here, I need to isolate my y, so I'll raise e to the power of both sides. And that cancels with the natural log. And this is actually just e to the ln x times e to the c3, because when you have two things added in an exponent, it's the same as two different terms sharing the same base, with those parts of the exponent multiplied by each other. So that means that the absolute value of y equals the absolute value of x times e to the c3. And this is just another constant, so I'll call that c4. Now, how do we get rid of these pesky absolute value signs? Well, we can just introduce a plus or minus. And plus or minus c4 can be just written as c4, because if c4 was to take the value of 1, plus or minus c4 would give us 1 times x, or negative 1 times x. However, if c4 was just negative 1, it would also give us the same. So that means that we can get rid of this absolute value, this plus or minus sign. And thus, this is the equation described by the separable equation dy over dx equals y over x. Now, whenever you solve a separable equation, a good idea is to then take the derivative of again, to then take the derivative and to see if that gives you the same part that you were starting with, y over x. So if I take the derivative of this guy, get dy over dx equals c4. And you may be thinking, wait a minute, that's a c4, that's not y over x. But look here, if we divide both sides by x, we get y over x equals c4. So c4 is indeed y over x. and this is the correct solution. Now, what is the point of having a separable equation though? A separable equation actually describes the slope field of a graph. So if I have the graph, the slope of the tangent line to the graph of f of x is, let's just say y over x, because that was the previous problem. This is saying the slope of the tangent line, or the change in y and the change in x, which is dy over dx, is equal to y over x. So the question is, the differential field of a graph in the xy plane is given such that the slope of the tangent line to the graph at x comma y is 1 plus the square root of x all squared over 1 plus the square root of xy plus the square root of x plus the square root of y. Find the equation that describes the graph if it passes through the point 0, 9. So the first thing that we can see is, because the slope of the tangent line is given by this equation, we can just write dy over dx equals this thing, and we thus have set up our separable equation. But at first glance, this thing doesn't really seem separable, right? There's a x times y here in the denominator, and there's a whole bunch of other x's and y's added together. So some people might think, oh, maybe we should multiply both sides by this denominator and then subtract off the x and the x terms, so leaving the y terms on the left side. But this doesn't really work, because there's going to be a xy term over here, and there's also going to be a dx. So we can't just integrate something in y with respect to x normally, as in this case x plus y, we would get x squared over 2 plus xy plus c, because y is related to x. It's a function of x. So we're not considering its derivative right here. For example, if I plug in y equals 2x, I would get f of 3x dx equals 3x squared over 2 plus c. And if I plug it in here, I get 5x squared over 2 plus c. These things aren't equal. And that's because we don't consider the derivative of y when taking this integral. So that doesn't work. Instead, we need to find a way to separate the x's and y's purely in terms of multiplication. And we basically need to write it as g of x times f of y. So what do we see when we look at the top? The top is just x's, so that's good. That can be separated into an x. But the bottom is a mixture of x's and y's. And now we need to use a well-known mathematical fact known as Simon's favorite factoring trick, which says that if I have 1 plus a times b plus a plus b, that can be factored into 1 plus a times 1 plus b. In this case, a equals the square root of x and b equals the square root of y. That means that I will get this is equal to 1 plus the square root of x times 1 plus the square root of y. And now we can multiply both sides by 1 plus the square root of y and dx, and we'll have separated the x's and y's. So doing that, we get 1 plus the square root of y dy equals 1 plus the square root of x squared over 1 plus root x dx. And these cancel because 1 plus root x and 1 plus root y, those are never going to equal 0 because they're always positive. Now we integrate, and we get y plus 2/3 y to the 3 over 2 plus c1 equals x plus 2/3 x to the 3 over 2 plus c2. And I'm going to do the same thing as before. I'm going to subtract c1 from both sides and call c2 minus c1 c3. So that is just this. And from here, you might be tempted to go, oh, this is y plus 2/3. Y to the 3 over 2, this is x plus 2/3. X to the 3 over 2, I can call that, just y and x, whatever. It's because when y equals x, this holds true. You can't do that because this is not a linear equation. This actually has a y to the 3 over 2 and an x to the 3 over 2. So it's going to have more than just one set of solutions. So we can't just say, oh, this is y and this is x. Now we have an equation, but we're not done because the problem says that it passes through the point 0, 9. So we need to plug in 0 for x and 9 for y to solve for our constant C3. So plugging 9 in for y and 0 in for x, we get that C3 equals 27. So that means our final equation that describes this graph is y plus 2/3 y to the 3 over 2 equals x plus 2/3 x to the 3 over 2 plus 27. And you can check by differentiating this as we did in the first part to see if dy really does equal this when you're done. So I hope you learned something. Thank you for listening.